There's nothing simple about simple AC circuits. We're going to talk about some rather difficult subjects, something that even electrical engineers, when they're first starting out, really have a difficult time visualizing. And this is going to be the idea of the phase of the voltage and the phase of the current, and something that we call a phasor diagram that shows us how the voltage is behaving in terms of its phase compared to the current. Okay, so let's get started with our simplest example here. And the simplest example here is going to be, of course, the resistor. So what we have here, and you'll notice that I represent an AC power source with a circle and a squiggle right here. I've hooked a resistor up to an AC power source. And the voltage is going to basically follow a sine function. Okay, it's going to go up and down, up and down, up and down. All right. We can write the voltage by this equation right here, where V0 represents the maximum voltage, as we saw for 120 VAC. V0 there would be about 170 volts. Omega is the angular frequency. It's related to the linear frequency, and the linear frequency is about 60 hertz. Okay, so I set that up. I say, all right, there's my voltage. How is this resistor going to behave? Okay, so I apply Ohm's law. V equals IR. The voltage is proportional to the current times the resistance. Okay, that works. I have voltage over here. I have current over here. So whatever the voltage is doing, the current is always going to be proportional to it, and proportional by some constant proportionality, which is R. Okay, so here we can see when the voltage peaks, the current peaks. When the voltage is zero, the current is zero. When the voltage drops to its negative value, the current is its most negative value. The two are effectively matching each other, peak for peak, valley for valley. We say that they're in phase because the peaks line up with the valleys. Whatever the voltage is doing, the current is doing the same, offset by some proportionality constant, which is, of course, your resistance. Okay, I is equal to V divided by R. Okay, so if my equation for the voltage looks like this, okay, my equation for the current is also going to have a sign in it. All right, so yeah, here's my voltage source. That's what this is doing right here. Here's my current. That's what it's doing right there. The peaks line up with the peaks, valleys line up with the valleys, and my current here, my maximum current, is just my maximum voltage divided by the resistance. Nothing complicated right there. All right. Now, because this is the simplest example, I want to show you the phasor diagram for this. Okay. Instead of graphing the voltage and current like we see right here, I'm going to graph them using a rotating plot that we call a phasor diagram. Okay, here's how it works. We can imagine that on this diagram, the vertical direction, in this particular case, they're using vertical direction. Sometimes they'll use a horizontal direction. But the vertical direction represents the current. And we can imagine that I have some vector I0, which is rotating around this axis, and that IR, okay, or IT, is basically the vertical projection or the vertical component of that rotating vector, okay? When the vector is down here, IR is 0. When the vector is here, IR is equal to max, it's equal to I0. So try to animate this in your mind, that this vector is going around. This vector is always the same length, okay, but it's spinning around in space. And the real current that I see is this vertical component that's sometimes pointing up and sometimes pointing down. Okay, now remember I said the current is in phase with the voltage. Well, on the previous example, the current was less, the way it was scaled, than the voltage. We imagine that both are represented by two vectors. Okay, and both of these are spinning around in time. Okay, and as long as they're in phase with one another, we are going to get peaks where we have peaks and valleys where we have valleys. All right, okay, I need to do a little reset right here because my image froze, but that's one of the fun parts of using Zoom, that if I start drawing something and something goes wrong, that image burns in, but I'm back to where I need to be. Okay, so whenever we have a circuit where we say the current and voltage are in phase, we can imagine the two vectors line up with one another and they both rotate with one another in space. And that gives you that, you know, peak to peak and valley to valley that we see right here. Okay. All right. Now, that's the simplest case for our phasor diagram. Let's imagine what happens with our capacitor, because things are going to be a little bit different here. Okay. If we think about our capacitor, we will have current flowing to our capacitor. Okay. We'll have current flowing to our capacitor as it charges. Our voltage, VT, is equal to the charge on the capacitor, QT, divided by the capacitance. Okay. So what that means is that the voltage is going to become maximum, okay, by the time the current stops dumping charge onto the two plates. All right, think about that. When the current stops, the charge is maximum and the voltage is maximum. What that means is that the current is not doing the same thing as the voltage is doing. Okay, what does this mean in terms of current and voltage? Well, again, remember, when we were charging a capacitor, the charge was increasing like this until it reached some maximum. Well, if we think about just charging a capacitor with a DC circuit, we could imagine that the slope of this would be dq dt, which is your current, okay? However, the slope goes to 0 when it reaches maximum charge. So really, looking at the current here, the current is the first derivative of the charge with respect to time, which means that it's going to be related to the voltage, but it's going to be a derivative of the voltage. All right, I don't know if that really helps you very much, but we can write I as dq dt. Q is equal to V over R, so we can rewrite it like this. And again, if I have an expression for VC, which we saw for a AC circuit, V is equal to V0, we use sine omega t. To get the current, we need to take the derivative of that, okay? The derivative of sine is cosine omega t, so that's V0. Oops, I should use I0 there. I'm not going to assume what the current is, but it is going to be out of phase with one another. All right. I know that looks a little bit like a sleight of hand, but for a capacitor, again, our slope here is related to the current, where our level here is related to the voltage. So what does that mean? Okay, think about this. We first turn on our source, okay? We first turn on our source, our voltage is 0, okay? That means that the capacitor is completely discharged, okay? There's nothing on it. As we start charging it, that's when the current's going to be maximum, okay? That's when we're going to have the most current. So I notice that my current is maximum here, but as it gets fuller and fuller, the current's going to become less and less until it's fully charged. So here, capacitor is fully charged. The current has stopped. Notice that the current is ahead of the voltage, okay? I know it looks like it's behind it, but if you think about time, the voltage peaks a quarter cycle after the current peaks. Okay, likewise, the capacitor is going to discharge, so the current's going to go the other way. When the current is at its maximum, the voltage has reached a 0, and then the current's going to stop again. Current's going to stop again when the polarity of the capacitor has changed to complete opposite direction. So I'm going to erase this right here. Now what we have is a positive charge on this side, and we have a negative charge on this side. Okay? So very clearly, if you want to do this mathematically or visually, very clearly, one can see what's going on here. The current is the first derivative of the voltage, okay? So we get this V0 over R cosine omega t, okay? Actually, I should have a 1 over R out here. Sorry that that disappeared there. But the derivative of sine gives me cosine, okay? Likewise, if we just think it out, we clearly see that down here in this graph, this is a sine function, right? That's a sine function, whereas this, the current, is a cosine function. Cosine is 1, where it's maximum at t equals 0. Okay, so let's do a phasor diagram for this one. Let's try to figure out what this is going to look like if we have sine here and we have cosine here, because cosine is sine omega t plus pi over 2 radians. That's one of the trig identities. Okay, so here what we see is that the current is ahead of the voltage by 90 degrees or pi over 2. Okay, so these two are going to be rotating together. Like a little bit later in time, your voltage vector will be here. Your current vector is still going to be 90 degrees with respect to that. Okay, it's still going to be 90 degrees with respect to that. And they're both rotating in space and make one complete rotation in one cycle. But because they're 90 degrees out of phase with respect to one another, okay, when one is peaking, the other one is going to be 0. And again, remember, in this phasor diagram, we're using the vertical direction as the current value for the voltage or current, the present. Okay, so what do we say for the capacitor? The capacitor, the current leads the voltage by 90 degrees when we look at this phasor diagram. Now, there's something important here that we call reactance, which helps us relate the amount of current that we get due to a certain voltage for the capacitor. Now, I incorrectly threw in resistance earlier on, but That was just more or less a placeholder because I hadn't gotten to reactance yet. But reactance should be thought of as being very, very similar to resistance. The units for reactance is the ohm, okay? And the reason why the units are ohms is it tells you how many volts are required to get a certain amount of current, okay? So if your reactance is 10 ohms, if I have a voltage amplitude of 10 volts, I will get a current of 1/10 of an amp, okay? So again, reactance is a very important concept because it really takes the place of resistance. There is no resistance in our capacitor, okay? So what is going to regulate the current? Well, the thing that regulates the current is how quickly the capacitor charges and discharges. Okay. Now notice that I've set the reactance equal to 1 over omega c. So omega, again, is our angular frequency, which is 2 pi times the regular frequency. Okay? But it also depends on the capacitance. All right. Think about this. Reactance is how much we're limiting the current. If the capacitance is very, very large, it's going to take a lot of current to charge this capacitor. So a big capacitor is going to have a small capacitive reactance. The other thing is the frequency. If I'm charging and discharging the capacitor very, very quickly, okay, then the current is also going to have to be very, very large. So if I make the frequency of my AC higher and higher, the reactance also drops. Okay, so what is capacitive reactance? Symbol is XC, X for reactance, C for capacitance. It really shows us how we can equate voltage and current to one another for the capacitor. As I said, this isn't simple. Okay, let's go on to the next. Oh, by the way, here's something that is interesting. If we graph reactance as a function of frequency, what we find is that the reactance is very, very high at low frequencies. In fact, if I set omega to 0, okay, with a frequency 0, it's basically DC, I get a reactance of infinity, which means that I is equal to the voltage divided by infinity, and that's equal to 0. That's saying that for a capacitor, you can't get current through a capacitor if there's no frequency. The frequency is 0, because it's an open circuit. Okay? But what we also see here is for lower frequencies, the reactance is going to be very, very high, which means you're not going to get a lot of current there. For higher frequencies, the reactance is going to be low, which means your current is going to be very much larger. Okay, I'm going to change colors. So essentially, a capacitor can act as a high-pass frequency filter. What does that mean, high-pass frequency filter? It means it's going to get rid of the lower frequencies, okay? And it's going to pass through the higher frequencies, okay? All right. Again, the reactance of a capacitor is 1 over omega c. What about our inductor? How is that going to work? Okay, we saw the resistor was in phase, so the current was in phase with the voltage. We saw for the capacitor that the current led the voltage by 90 degrees. What's going to happen with this inductor here? Okay, so we got to go back to some ideas that we covered earlier to understand this a little bit better. Remember when we defined self-inductance as the number of turns in a solenoid times the rate of change of the magnetic field, and that self-inductance was measured in henries, which told you how many volts divided by the rate of change of current. Okay, so let's rewrite this equation, not this part right here, but L equals E over di dt. So now we see that the EMF, or the voltage across the inductor, is going to go by L di dt. Okay. Now, when I turn a DC circuit on with just an inductor, we know that it's going to take time for the magnetic field to build up. So the current initially is going to start at 0, and then as the current gets going, the back EMF is going to be less and less. So I'm going to take this expression right here. I'm going to integrate both sides. Integrate the right side, I'm sorry, the left side, and I integrate the right side, and I get this right here. Okay. Now remember, the voltage for an AC circuit is going to depend on your sine function. So, think about that as we do this. So if I take my voltage, I plug in that V0 sine omega t, I take the antiderivative here, okay? And the antiderivative of sine is negative cosine. So negative V0 cosine omega t equals L times I, so I is equal to this. Okay, putting the calculus aside, let's look at this visually about what's happening. Again, when I first turn on the voltage, okay, and the voltage is ramping up, okay? Actually, you know where I need, I want to start? I want to start right here. Let's start right here. I put on the voltage, there's a back EMF. So it takes time for the current to build up, okay, to this maximum value right here until the voltage drops down. Now remember, when I first turn the circuit on, the total voltage is 0 because you have the voltage which is applied plus the back EMF that's going to add up to be equal to 0. So the current starts moving, and then it builds up in the inductor, and the back EMF goes away. In this case, we can clearly see that while the voltage is following the sine function, the current has this negative cosine function, which is 90 degrees behind my voltage. Yeah, notice this peak right here. Notice this peak. We have this peak right here in the voltage, and the current reaches its peak 1/4 of a cycle later on. So if I'm going to represent this with the inductor, it's going to be the exact opposite of what I had with the capacitor. Remember, the capacitor peaked right here, so it was 90 degrees ahead of the voltage. Now this is going to be 90 degrees later or behind the voltage for the current. So again, drawing our phasor diagram, now we still have both rotating, but my current is behind. It's instead of leading like it did for the capacitor, it's now 180 degrees in the opposite direction. Okay, so with an inductor, we lag. Our current lags the voltage by 90 degrees. Okay? And the reactance of an inductor is similar to the reactance of a capacitor in that it's also measured in ohms. It also tells you how much current you get for a certain voltage. But instead of being 1 over omega times C, it is omega times L. What does this mean? It means that as a frequency gets higher, this inductor with its back EMF is going to resist the change in the magnetic field. And the larger the inductance is, the greater that resistance is going to be. So an inductor acts just the opposite way that a capacitor does, meaning its reactance gets larger with a higher frequency. So in some ways, we can picture our inductor as letting low frequencies pass, but blocking higher frequencies because it doesn't allow the current due to this reactance. Okay? So again, looking at this, to summarize the major points here, first of all, this concept of a phasor diagram. The phasor diagram tells you what the current is doing with respect to the voltage. It's an easier way to picture what's going on. And if we go all the way to the resistor, our resistor is the easiest case where the current and voltage are oscillating in phase with one another. They're moving together. When the voltage goes up, the current goes up for the resistor. For the capacitor, the current's ahead of the voltage. We look at its phasor diagram, and the current is 90 degrees ahead. Okay? And also, its reactance, okay, is inversely proportional to the frequency. So capacitors, they love high frequencies. They don't like low frequencies. The inductor, just the opposite. The current is 90 degrees behind the voltage, and also the reactance is proportional to the frequency. So an inductor, it loves a low frequency. In fact, if you put DC through it, the inductor will not do anything to interfere with the flow of current. Okay, just the resistance of the wires. So think about this as we go forward. We're going to see what happens when we combine inductors, resistors, and capacitors, and talk about something called a phase angle. This phase angle is 0 for the resistor. It is plus 90 degrees for the capacitor and negative 90 degrees for the inductor.